Hey everyone, just wanted to make a video going over patterns for derivative and integral rules that may help you as you're preparing for your AP exam, and having to know all these rules sometimes can be a little daunting. So I just want to kind of start off with trig derivatives. These rules, I really encourage you guys to be able to write these rules down at the top of your multiple choice non-calculator portion. That's going to be the first portion that you take, and the likelihood of these rules coming up is showing up is going to most likely be during that multiple choice non-calculator portion. So I just want to kind of show that if you are able to write the derivative rules down in this order, there are some nice patterns that hopefully will help you memorize them a little quicker, a little faster, a little more efficiently. Okay, so sine and cosine, these are rules that we've used a lot over the course of this year. So these are kind of like the basic ones, right? Sine's derivative is cosine of u times u prime. Cosine's derivative is negative sine of u times u prime. Okay. Okay, now moving on to tangent and cotangent. These derivatives kind of have similar forms. And so tangent's derivative is secant squared u times u prime. And then cotangent's derivative is negative cosecant squared u times u prime. Okay, secant and cosecant, these are across from each other. They have a similar pattern as well. Secant's derivative is secant u tangent u times u prime. And cosecant's derivative is negative cosecant u cotangent u times u prime. Okay, so the ones that are next directly across from each other, they kind of share similar patterns. I also want to show you a couple of things here. Tangent and secant, their derivatives basically just involve only each other, right? Tangent just involves secant squared, and then secant's derivative is just secant tangent. So these derivatives just basically involve each other, right? Cotangent and cosecant, their derivatives basically just involve each other as well, if you look at them. Sine and cosine, these derivatives basically just only involve each other. All right. Some other nice patterns about this setup is look at all these functions on the right side. These all begin with c, and all the c functions produce a negative derivative. So that's something nice to have that lined up, so you know that you won't have to question whether a derivative is negative or not, if you remember that, okay, all the c functions are the ones that produce negative derivatives. And also I have these c functions are in alphabetical order as well. Okay, so hopefully listing out those patterns can help you remember these rules a little faster. And there's also another reason why I would like for you guys to be able to write these down at the top of your multiple choice exam as soon as you get your exam, is that these may only look like there's 6 rules, but there's actually 12 rules here. There's 6 derivative rules, but then there's also 6 integral rules, and I want to show you how we can arrive at those rules. Okay, so remember, with integral rules, we're just going backwards, right? We're undoing the derivative process. So let me show you what we can do here. Okay, so basically, if I just put integral notation, on the right side, then that basically leads me to my integral rule. The integral of cosine is just going to be sine of u plus c. So I have this on a separate page that I'm going to just go ahead and fill out. But there's no need for us to memorize these integral rules, because if we just write these derivative rules down, we can just arrive at them by working backwards from our derivative rules. So integral of cosine is going to be sine of u plus c. So I'm going to put that here. Okay. What about the integral of sine? The integral of sine, okay, if you put your integral notation right between the negative sign and the sine of u, then basically anything the integral sine of u is just anything to the left of it. So that negative is going to have to go with that cosine. So integral of sine is just going to be negative cosine u plus c. Okay. Going down the line here, the integral of secant squared u is just tangent u plus c. The integral of secant u tangent u du is just going to be secant of u plus c. The integral of cosecant squared u, that negative is going to have to go, has to be accounted for, so it's going to go with the cotangent on the left side. So integral of cosecant squared u is just negative cotangent u plus c. And then finally, the integral of cosecant u cotangent u du is just negative cosecant u plus c. Right, so there's no need to memorize these basic trig integral rules. We can directly arrive at them just by using the derivative rules that we've memorized. Okay. Okay, let's see. Going down the list here. Next, logs and exponential derivatives. Now, these ones we need to know. Hopefully, we've seen these enough where we know them. Natural log of u's derivative is just u prime over u. These are one of the most common ones that we come across. The derivative for e to the u is e to the u times u prime. You're almost guaranteed to see these on the AP exam. Now, these are less common, log base a of u and a to the u, but I want to put them directly below these, because I think of these as kind of parent derivatives or parent functions, and these are just functions that are kind of based off of the ones above it. So log base a of u, okay, this is natural log is log base e, but log base a is also a log function, just a different base, and base a just represents bases other than e. Could be base 2, could be base 3, could be base 4. Okay, and I want to show you that the derivative rule looks a lot like the natural log. There's just a little bit extra to deal with, to handle the conversion that needs to happen. So log base a of u, hopefully that reminds you of natural log of u. They're both logs. So there is a u prime over u component. So that's nice to know that log base a of u is also going to have that the rule that we hopefully already know. And the only adjustment is this does require a 1 over natural log of a. It's a bit of a conversion that has to occur. Get this in terms of natural log, and then u prime over u. Okay. Now, e to the u we know is e to the u times u prime, just the original function times the exponent's derivative. A to the u is an exponential function that's base a. So it could be base 2, could be base 3, could be base 5. So I want to kind of put these above each other to show that these are very similar to each other. e to the u is the original function times exponent's derivative. A to the u, very similar. There's also the original function times the exponent's derivative. But it's not base e. So it's not base e. There's a conversion that has to occur, and it's going to take on the form of natural log of a as a coefficient. Okay, so this one has a coefficient of 1 over natural log of a. This one has a coefficient of natural log of a. And the next question you may be thinking is, oh, these look very similar. What if I get these mixed up? You know, how do I know which one's the numerator, which one's the denominator? So the way that I remember it is, I know that there's natural log involved because this is base a, not base e. And the way I know to help me remember that this doesn't go in the denominator is because the rest of my expression doesn't show any denominator. So if there's no denominator, I know, okay, all right, that natural log of a is going to have to go up in the numerator. Now, log base a of u, my derivative rule reminds me of natural log of u prime over u. There's a denominator portion. So that denominator portion reminds me, okay, that natural log of a is going to have to sit in the denominator. Okay, so that's how I remember. The rest of the expression has no denominator, therefore natural log of a stays up. The rest of the expression does have a denominator, so that reminds me the natural log of a is going to go below. Okay, next up are the arc-trig derivatives. What I want to show you is that we basically only have to worry about arcsine, arctangent, arcsecant, because the one directly across from them are just the negative versions of the corresponding ones to the left of it. Okay, and also I organized these the same way that we did trig functions. I just basically, just imagine just putting arc or inverse in front of those corresponding names. Okay, so I want to talk about pattern to hopefully help you memorize these rules. So with arcsine, arctangent, arcsecant, all of them have numerator and denominator. Okay, and their numerator look exactly the same. All the numerator is just u prime. So I'm going to put that like this. They all have u prime in the numerator. Okay, now the denominator is different, but all the denominators involve so all denominators have a 1 and a u squared. Okay, they all have 1 and they have u squared, just different orientation, different way that they're organized, but just nice to know that, okay, I just have to figure out how that pattern looks. There's just going to be a combination of 1 or u squared. Okay, so when I create this, if I have a separate sheet of paper on the exam, I like to write these 3 down because, and the way I remember them is I start with the easiest. Arctangent is the easiest one. This is also the one that if there's the highest chance of arc-trig function showing up, it's going to be arctangent. Okay, it's going to be, so this is the one that looks the cleanest, the easiest one. It's just 1 and u squared with a plus in between. So it's just going to be 1 plus u squared. All right. So it's clean. There's no minus sign. There's no square root. There's no absolute value. Okay. So the next thing I like to write down is I like to write down the arcsecant. Arcsecant is the most complex looking one. Okay. So arcsecant has an absolute value of u in front. It's got a square root, and it's got u squared and 1. The complexity that looks strange is the fact that there's a minus sign. And the next decision that I have to make is, all right, which one comes first? Is it going to be 1 or is it u squared? And it's going to be u squared coming first, minus 1. And the way I remember that is I know that the u's are next to each other. So I know there's an absolute value of u, there's square root of u squared. I know that the u's are next to each other, and that helps me remember the order. Okay. And I like to write the arcsecant first because having the u's next to each other, that's an easy way for me to remember that pattern. Arcsine, I save this for the last one to write down because arcsine and arcsecant look very similar. It's easy to get these mixed up because they both have square roots, they both have a minus, they both have a 1 and u squared, but I know that it's going to look slightly different from arcsecant. So arcsine does not have the absolute value, it's got the square root, it's got the 1 and the u squared, but I know that it's different. I know the pattern is going to be different because this is u squared minus 1. The pattern here is going to be 1 minus u squared. Okay, so that's how I kind of go through this process of writing down these rules. It looks messy when you first look at it, but hopefully after going through those patterns and similarities and the order that I write them down, hopefully that helps. Okay, so once you have these down, you know these three are going to be easy because we're just going to copy the ones directly across, but we're just going to put a minus sign, just like how we experienced trig functions starting with c producing negative. All these arc trig functions that have c's in them, like cosine, cotangent, cosecant, they all are also going to produce negative versions. So. All right. Okay, so I have a second page involving integral rules. We filled out the top because these are just basically they're based off of the derivative trig rules that we just talked about. Okay, let me save these for last. Power rule, logs, exponentials. So power rule for integrals. All right, so this one we should know already. Guaranteed to show up. Power rule shows up a lot. Derivative and integrals. Okay, so e to the u and 1 over u. These are based off of what we've seen from these derivative rules. We know the integral of e to the u is just going to be e to the u. The integral of 1 over u is just natural log of u plus c. So these are also very common, and we should know them well because we've seen so much of it. Okay, so 1 over u, integral 1 over u, natural log absolute value of u plus c. Okay, e to the u, just e to the u plus c. Okay, this is less common, but what I want to do is I want to bring you to the rule that we learned on the derivative side of things. Right, we learned on the derivative side of things that the derivative of a to the u is natural log of a times a to the u times u prime. So just like how we were working the other rules with integrals, we're just working backwards. So let's say we just let's say we want to just derive it from the rule that we have here. We know we're going backwards, so if you can put an integral notation between natural log of a to the u, you know that integral of a to the u is just going to be everything to the left of it. However, this natural log of a has to end up being divided over, so that's why it's going to end up looking a to the u over natural log of a. So therefore, the integral of a to the u, that natural log of a is going to have to dip below in the denominator. So it's going to be a over u over natural log of a plus c. Okay. What I like to do is I like to sometimes push the coefficient out in front just so that it just feels a little bit cleaner, but they are the same. Okay. Inverse trig integrals. These, I think, as long as we're able to see that there's a lot of similarities here. Okay, so think of a as a constant. So a kind of matches up with the 1. So a squared minus u squared is going to be the u squared is coming second. There's a square root. It's going to be involved with arcsine. The a squared plus u squared has no radical in the denominator. It kind of looks like this, so we know that working backwards, it's going to be involving arctangent. And finally, we got the u outside, we got the square roots. U's are next to each other. This is going to be involving arcsecant. Okay. But there's a slightly different variation to the integral rules that make it a little messier. There is a coefficient that we got to keep track of, except for the sine. Arcsine does not have a coefficient, so it's just going to be, yeah, so these are not quite as clean in terms of working backwards, but at least we see some similarities. It's just going to be arcsine of u over a plus c. Okay, we know that this is involved with arctangent, but there's a coefficient in front. There's a 1 over a arctangent of u over a plus c. Right. And finally, arcsecant is just natural. It's just the messiest looking one. It's got 1 over a arcsecant. There's an absolute value that's going to have to be part of our integral rule. Absolute value of u over a plus c. Okay, thankfully, these rules don't show up that often from previous AP exams that I've seen. I've seen this show up, so if you're having trouble memorizing them, if you can memorize this one, then there's a good chance that if one does show up, this is the one that's most likely. But if you're able to, it's great to have all these memorized. Okay. Finally, we have trig rules involving natural log. So these are trig rules that are not based off of the original 6 that we learned on the derivative side. So these just, yes, I say these for last because these are just ones that are just the most difficult to remember. So there's actually a way to derive them, and I'm not going to go through how it's derived, but the way I remember it is there's a little bit of U substitution going on, and I think of tangent as sine over cosine. And if you think of this as a U substitution, which I'm not going to go over right now, but basically, if you let the U value be that cosine, that's what's going to show up in the natural log rule. Okay, and also cosine produces a negative derivative. Cosine produces negative derivative, so there's a negative involved here. So it's negative natural log absolute value of cosine of u plus c. All right, so that's hard to remember, but if I think in terms of sine over cosine and use substitution, and cosine's derivative produces negative sine, that's where that negative comes from. This rule, I think a lot of students have trouble with because tangent, we just don't associate tangent with negatives because on the derivative side, we're used to seeing C functions producing negative. We're not used to seeing, we don't recall tangent involving negatives. So this one just seems a little bit out of place with that negative, but that's the cosine is what's causing that negative. Now cotangent, the way I remember cotangent is, okay, I know cotangent is cosine over sine, and that U substitution that goes on is forcing that to be the U value. So that's what shows up in my natural log rule. Sine's derivative is a positive cosine, so there's no sine, there's no negative here, so natural log absolute value of sine of u plus c. And so that feels a little bit opposite. We associate cotangent with negative, we associate tangent with positive, but yeah, this feels a little bit different here. Okay, secant and cosecant, I just think in terms of what's involved. When I think of secant, I think of secant tangent. When I think of cosecant, I think of negative cosecant cotangent. And so that's basically it. I don't have a way of deriving them, but just the pattern, it's nice to see patterns that we recognize. So secant of u is not one of the original 6. There's a natural log involved. It's natural log of, but it's going to involve secant and tangent, but it's going to be a little bit different. There's going to be a plus in between instead of a multiplication. And then cosecant, similar to what we would expect. Cosecant, we naturally expect it to produce a negative integral, and that's the same. That's what's going to happen here. It's going to be negative natural log absolute value. Cosecant we associate with cosecant and cotangent, but instead of multiplication, it's going to be added. Okay. All right, so I will provide a link under this video, and the link has blank copies, which I filled out here, as well as the full rules. So if you need some extra practice, you can print this out, and hopefully having these patterns laid out will make it a little bit faster for you guys to, or quicker for you guys to memorize them.